High above us, drifting through the inky blackness of space, there's a place where the rules of the universe seem to bend, or maybe even break. The Small Magellanic Cloud, a ghostly dwarf galaxy clinging to the edge of our Milky Way, is home to cosmic oddities that defy everything we thought we knew. Imagine a celestial graveyard where stars don't just fade, they vanish without a trace. A place where mysterious objects glow with energies we can't explain, and structures appear where none should exist. And now, astronomers have uncovered 30 of these enigmas, each one more baffling than the last. This isn't just a story about distant space, it's a puzzle that could rewrite the textbooks. For centuries, the Small Magellanic Cloud has been a silent companion in our night sky, a smudge of light visible only from the southern hemisphere. But behind that faint glow lies a realm of chaos and wonder. Unlike the orderly spiral of our Milky Way, this dwarf galaxy is a turbulent, star-studded wilderness, a place where cosmic collisions and explosive stellar deaths have left behind a trail of bizarre relics. Some of these objects pulse with rhythms we've never seen before, while others emit signals that shouldn't be possible under known physics. And the strangest part, no one can agree on what they really are. Are they remnants of ancient supernovas, secret hideouts of rogue black holes, or something even more extraordinary? Tonight, we're embarking on a journey to the edge of understanding. These 30 anomalies aren't just scientific curiosities. They're keys to unlocking secrets about the birth and death of stars, the fabric of space itself, and maybe even the fate of our own galaxy. Some of them flicker like cosmic lighthouses, others lurk unseen, bending light around them like celestial ghosts, and the closer we look, the more questions they raise. So buckle up, because by the time we're done, you'll never see the night sky the same way again. The Small Magellanic Cloud isn't just a neighbor, it's a mirror reflecting back the mysteries we're only beginning to grasp. One of the most mesmerizing yet puzzling sights in the Small Magellanic Cloud is the ghostly nebula known as NGC 346. This glowing expanse of gas and dust shouldn't look the way it does. Its delicate, wispy filaments twist through space like cosmic cobwebs, illuminated by an otherworldly blue radiance. But what's truly baffling isn't just its haunting beauty, it's the way this nebula defies the rules of star birth. Nestled within those swirling clouds are some of the most massive young stars ever observed, burning with such intensity that they shouldn't have formed under current scientific models. Theoretical predictions suggest stars this colossal shouldn't exist here, where the galaxy lacks the heavy elements needed to stabilize them. Yet there they are, blazing defiantly, as if the universe itself is rewriting the textbooks on stellar evolution. Hubble's breathtaking images reveal even deeper mysteries. The nebula's structure resembles a spider's web stretched across the void, with tendrils of gas stretching light years into the darkness. These filaments shouldn't hold together so elegantly without the gravitational glue of heavier elements. They should have dissipated long ago. Instead, they cradle newborn stars like celestial nurseries, their delicate threads somehow resisting the violent stellar winds tearing through them. Some astronomers speculate hidden forces are at play, perhaps unseen magnetic fields weaving this cosmic tapestry tighter than physics allows. Others wonder if we're witnessing an entirely new mode of star formation, one that thrives in the Small Magellanic Cloud's chaotic, metal-poor environment. What makes NGC 346 even stranger is its eerie glow. Unlike typical nebulae, which shine primarily from reflected starlight, this one pulses with an unnatural blue hue, as if lit from within by an unknown energy source. The phenomenon has led to wild theories. Could there be exotic particles at work, or even remnants of an ancient cosmic event we've yet to understand? Every time we point a telescope at this nebula, it reveals another layer of mystery, challenging our assumptions about how stars are born and how the universe operates in its most remote corners. NGC 346 isn't just a star factory, it's a laboratory for the impossible, testing the limits of what we know. And the deeper we look, the more it feels like this ghostly structure is hiding secrets we've only begun to glimpse. If NGC 346 is a cosmic ghost weaving mysteries, then NGC 265 is its rebellious counterpart, a star cluster hurtling through space with reckless abandon. This compact family of stars isn't just drifting, it's racing through the Small Magellanic Cloud at speeds that defy logic, as if flung from some distant cosmic slingshot. Astronomers call it a runaway cluster, and for good reason. Its velocity suggests it didn't originate here at all. Instead, it might be a fugitive ejected from another galaxy entirely, now streaking through its adopted home like an interstellar outlaw. What makes NGC 265 truly extraordinary are the stars within it, blue supergiants so luminous they outshine entire star systems. These colossal stars burn hot and fast, their brilliant blue light cutting through the surrounding dust like cosmic beacons. Normally, such massive stars are rare and short-lived, but here they cluster together in a dazzling display, their combined brilliance acting as a celestial fingerprint. By studying their light, astronomers can trace the cluster's path backward through time, piecing together a turbulent history of galactic collisions and gravitational chaos. The data tells a story of violence, a moment, perhaps billions of years ago, when this cluster was torn free from its birthplace and sent careening across the cosmos. Yet the mystery deepens when we consider how NGC 265 behaves today. Most runaway stars travel alone, but this cluster has stayed intact, its gravitational bonds resisting the forces that should have ripped it apart. How did it survive such a violent journey? Some theories suggest it was ejected during a close encounter between galaxies, a celestial near miss that sent it flying while keeping its stars tightly knit. Others propose it was once part of a much larger structure, a fragment left behind after a catastrophic collision. Every observation adds another twist to the tale, blurring the line between known physics and the uncharted rules of intergalactic escape. The blue supergiants themselves are another puzzle. Their brightness isn't just a clue to the cluster's origins, it's a window into the Small Magellanic Cloud's chaotic environment. These stars shouldn't thrive in a galaxy so lacking in heavy elements, yet here they blaze defiantly, their existence challenging our understanding of how stars form in metal-poor regions. Are they the product of some exotic stellar recipe, or do they hint at a hidden reservoir of materials we've yet to detect? The more we learn, the clearer it becomes NGC 265 isn't just a runaway. It's a rebel with clues, its high-speed flight carrying secrets about the forces that shape not just galaxies, but the universe itself. Amid the cosmic oddities of the Small Magellanic Cloud, there's a stellar corpse that refuses to follow the rules. Supernova Remnant 1E0102.2-7219. This twisted wreckage, forged in the death throes of a massive star, should have been a symmetrical shell of debris expanding evenly into space. Instead, it's a lopsided tangle of oxygen-rich filaments, glowing like a celestial firework frozen mid-explosion. Chandra's X-ray vision reveals a chaotic core where temperatures soar to millions of degrees, painting a portrait of an explosion that defies conventional models, one so powerful it might have rewritten the very physics of stellar death. What makes this remnant so baffling is its composition. Unlike most supernova remnants, which scatter a mix of heavy elements, this one is dominated by oxygen, a pristine layer of stardust that shouldn't exist in such purity. The star that created it likely tore itself apart in a way we've rarely witnessed, shedding its outer layers before detonating in a way that left oxygen as its primary fingerprint. Some theorists argue it was a rare pulsational pair instability, supernova, a runaway thermonuclear event so violent it pulses like a cosmic time bomb before the final collapse. Others suggest the star was spinning at breakneck speeds, distorting its explosion into this bizarre, asymmetrical shape. Chandra's X-ray data deepens the mystery. The Remnant's core crackles with turbulent energy, its shock waves rippling outward in uneven, starburst-like patterns. These aren't the smooth, predictable rings seen in textbook supernova. They're jagged, almost purposeful, as if the explosion was sculpted by unseen forces. Magnetic fields, a hidden companion star. The debris even seems to clump in ways that suggest it's interacting with invisible structures in the surrounding space. Every new observation sends researchers back to their models, questioning whether we've underestimated the diversity of ways stars can die. The most tantalizing clue lies in the remnants' motion. Unlike most supernova remnants, which expand steadily from a central point, 1E0102.2-7219 is hurtling through the galaxy at an unusual speed, dragging its twisted debris behind it like a cosmic comet. This raises a provocative question: was it kicked by the force of its own explosion, or did it inherit momentum from a binary partner that vanished in the blast? Either scenario challenges our understanding of how supernova distribute energy, hinting at forces far more complex than our current equations can capture. This remnant isn't just a relic of destruction, it's a manifesto, written in oxygen and X-rays, declaring that the universe still holds explosive secrets we've yet to decode. In the shadowy depths of the Small Magellanic Cloud, where most cosmic drama unfolds in blinding starlight and violent explosions, there exists a quieter, colder mystery: LERS 49 and LERS 72. These twin dark clouds drift through space like cosmic ink blots, so dense and frigid they blot out the stars behind them. To the naked eye, they appear as nothing more than voids, patches of emptiness where the galaxies glow simply. But peer through the infrared eye of telescopes like Spitzer or Webb, and these inky blobs transform into something extraordinary: cradles of creation, where the next generation of stars is already taking shape. What makes these clouds so fascinating is their defiance of expectations. In a galaxy as chaotic and metal-poor as the Small Magellanic Cloud, such dense, cold structures shouldn't hold together long enough to birth stars. Yet infrared observations reveal a hidden truth: nestled within these pitch-black folds are dozens of protostars, fiery infants wrapped in thick cocoons of dust. Their heat, invisible to optical telescopes, paints a glowing roadmap in infrared, tracing the earliest stages of stellar life. Some of these baby stars are so young they haven't even ignited nuclear fusion yet, their light smothered by the very material that feeds their growth. The contrast between darkness and hidden light is just the first puzzle. These clouds are far colder than similar nurseries in our Milky Way, with temperatures hovering just a few degrees above absolute zero. Normally, such extreme cold would stifle star formation, preventing gas from collapsing under its own gravity. But LERS 49 and LERS 72 thrive, their chemistry sculpted by the Small Magellanic Cloud's unique environment. Without heavy elements to act as cooling agents, their molecules rely on simpler processes to shed heat, creating a slower, more deliberate dance of collapse. It's a cosmic paradox. These clouds are both too cold and too fragile to exist, yet here they are, rewriting the rules of stellar birth. Even more intriguing is the way these twins differ from each other. LERS 49 is a sprawling labyrinth of filaments, its structure woven by magnetic fields into delicate, thread-like tendrils. LERS 72, by contrast, is a compact knot of turbulence, its innards churned by shockwaves from nearby supernova. This duality suggests there's no single recipe for star formation in this galaxy, just a chaotic mix of forces shaping each cloud into something unique. Some protostars here may grow into massive blue giants, while others will flicker to life as modest red dwarfs, their fates sealed by the subtle interplay of density and motion within the dark. The real revelation lies in what these clouds tell us about the galaxy's past and its future. Their mere existence hints at an invisible scaffold of molecular gas, a hidden backbone of the Small Magellanic Cloud that fuels star birth even in its sparse outer reaches. Every new infrared scan peels back another layer, uncovering more protostars, more filaments, more clues about how galaxies with so few heavy elements manage to keep the cosmic cycle of life and death turning. LERS 49 and LERS 72 aren't just dark spots on a star map. They're living proof that even in the quietest corners of the universe, creation persists shrouded in darkness but pulsing with the promise of light. Among the chaotic scatterings of stars in the Small Magellanic Cloud, one structure stands out with eerie precision: the ring-shaped cluster NGC 330. Unlike the typical globular clusters that huddle in messy, spherical swarms, this one forms a near-perfect circle, as if drawn by a cosmic compass. The symmetry is so striking it feels almost unnatural, a celestial fingerprint left by forces we're only beginning to comprehend. Most globular clusters are ancient relics, their stars bound by gravity in a tight, chaotic dance. But NGC 330's stars orbit in a synchronized loop, a stellar carousel spinning silently in the void. How did this ring of stars come to be? One theory points to a catastrophic collision, an encounter so violent it could have ripped through the cluster's heart, scattering its stars outward in a shockwave that froze into this perfect geometry. Picture two clusters barreling into one another, their gravitational tides stretching and sculpting the survivors into this improbable shape. Computer simulations suggest such encounters are rare but possible, leaving behind structures that defy the usual rules of stellar crowds. Yet there's another, even more dramatic explanation. What if NGC 330's ring was forged by a supernova, not just any stellar explosion, but one of titanic proportions? In this scenario, the blast wave from a dying star could have acted like a cosmic cookie cutter, carving a hollow sphere into the surrounding gas and dust. Over time, new stars would have formed along the edge of this bubble, leaving behind the luminous hoop we see today. This would make NGC 330 not just a cluster, but a fossil, a preserved echo of an explosion from an era when the Small Magellanic Cloud was young and volatile. The evidence hides in the stars themselves. Spectroscopy reveals that many of NGC 330's stars are unusually young for a globular cluster, burning hot and blue against the darkness. Their chemistry also hints at a turbulent past, with traces of heavy elements that suggest they formed from material enriched by earlier generations of stars. If a supernova did sculpt this ring, those elements could be the fingerprints of the explosion, scattered like cosmic breadcrumbs for us to follow. But the mystery deepens when we study the ring's motion. Unlike most clusters which drift lazily through their galaxies, NGC 330 seems to ripple with subtle internal movements, as if still settling from whatever event shaped it. Some stars race along the ring's edge, while others hover almost motionless at its center, a dynamic imbalance that shouldn't exist in a quiet, ancient structure. It's as if we're catching this cluster mid-transformation, a snapshot of cosmic evolution frozen in time. The implications stretch far beyond this single ring. If collisions or supernova can sculpt clusters into such precise forms, what other shapes might lurk undiscovered in the cosmos? And what does NGC 330's youthfulness say about the Small Magellanic Cloud's ability to keep birthing new stellar families, even in conditions that should stifle them? Every answer we find only peels back another layer, revealing how much we still don't understand about the forces that mold the universe's grandest structures. NGC 330 isn't just a curiosity, it's a challenge, a cosmic puzzle begging us to rethink everything we know about how stars gather, collide, and endure. Tucked away in an unremarkable corner of the Small Magellanic Cloud floats a celestial oddity that looks like a mistake, a glowing blue smudge adrift in the blackness, officially catalogued as DML 106. This so-called blue blob shouldn't exist. It's not a nebula, not a star cluster, just an isolated pocket of hydrogen gas burning with an intense azure radiance that defies all expectations. Most hydrogen clouds emit faint red light when energized by nearby stars, but DML106 shines like a sapphire dropped onto velvet, its color so vivid it baffles astronomers. What could possibly be powering this lonely cosmic lantern? The first clue lies in its surroundings, or rather, the lack of them. Unlike typical emission nebulae which cluster near young, hot stars, the blue blob floats in splendid isolation. No visible stars illuminate it, no supernova remnants pump energy into it. Yet spectroscopic analysis reveals the gas is being excited somehow, heated to temperatures that make it glow blue instead of red. Some researchers speculate it might be the ghostly aftermath of a supernova that faded from view centuries ago, its shockwaves still rippling through this cloud like invisible hands stirring a luminous pool. Others propose a more tantalizing possibility. What if a hidden stellar engine lurks within the gas itself? A neutron star or black hole, perhaps, spinning silently and bathing the hydrogen in high-energy radiation we can't directly see. Hubble's sharp eyes have revealed even stranger details. The blob isn't just glowing, it's structured. Delicate tendrils of gas spiral outward from its core, suggesting magnetic fields or turbulence shaping its form. These filaments move at velocities that shouldn't be possible for a simple gas cloud, hinting at powerful forces acting from within. One daring theory suggests DML106 might be a relic H2 region, a pocket of gas that once surrounded a massive star. When that star died, its ultraviolet light ceased, allowing the hydrogen to cool and collapse until something recently reignited it. Could a companion star previously overshadowed have flared to life? Or is this the signature of a rogue black hole accreting matter and lighting up the gas from the inside out? The most fascinating twist comes from the blob's chemical fingerprints. The Small Magellanic Cloud is notoriously poor in heavy elements, yet DML106's spectra show unexpected traces of oxygen and nitrogen elements typically forged in stellar cores and scattered by supernova. This raises a provocative question. Was the blob seeded by a nearby stellar explosion we've yet to identify? Some astronomers are scouring old radio observations for hints of a long-dead star, while others suggest the elements might have drifted in from elsewhere, carried by galactic winds over millennia. Every answer only leads to more puzzles. Why does the blob maintain its shape without dispersing? What keeps it shining so brightly without an obvious power source? And why does its light flicker subtly over time, as if something inside is breathing? DML106 refuses to fit neatly into any existing category, standing instead as a testament to how much we still don't understand about the quiet corners of galaxies. It's not just a mystery, it's a mirror, reflecting back how much of the universe's magic remains hidden in plain sight. Among the 30 cosmic oddities in the Small Magellanic Cloud, SMC-X1 stands out as a cosmic vampire, a neutron star locked in a deadly dance with its stellar companion, slowly devouring it alive. This X-ray binary system crackles with violent energy, its neutron star spinning so fast it blurs the line between physics and fantasy. Every second, it siphons gas from its neighboring star, creating a swirling disk of superheated plasma that glows with the intensity of 10,000 suns. But what makes SMC-X1 truly bizarre isn't just its appetite, it's the way it pulses with a rhythm that defies all expectations. Most X-ray binaries follow predictable patterns, their neutron stars emitting steady ticks like cosmic metronomes as they consume material. But SMC-X1's pulsations are erratic, speeding up and slowing down as if the star itself can't decide how fast to spin. Some days, its X-ray flares spike unpredictably, flickering like a candle in a storm. Others, it falls eerily silent, as if the feeding frenzy has abruptly paused. This strange behavior suggests it's accretion disk, the swirling funnel of stolen gas isn't behaving the way textbooks say it should. Instead of smoothly spiraling inward, the disk might be warped, fractured, or even flaring in chaotic bursts that destabilize the neutron star's rotation. The culprit could be the companion star itself, a massive blue supergiant whose fierce stellar winds don't flow evenly into space. Like a capricious fountain, it might spew gas in clumps and streams, feeding the neutron star in fits and starts rather than a steady trickle. This would explain why SMC-X1's X-ray emissions vary so wildly. It's not just dining, it's feasting on a cosmic buffet served in unpredictable portions. Some astronomers suspect magnetic fields are twisting the disk into strange shapes, while others argue the neutron star's gravity is so intense it shreds incoming gas into turbulent waves before it can settle into an orderly flow. Then there's the spin. SMC-X1 rotates at a dizzying 700 times per second, so fast its surface moves at nearly a quarter the speed of light. At this rate, the neutron star should be tearing itself apart, yet it remains intact, held together by gravity so strong it bends the rules of physics. Even stranger, its spin rate changes over time, sometimes accelerating without warning. This could mean the accretion disk is dumping huge amounts of energy onto the neutron star's surface in sudden, uneven surges, like a top being flicked by an invisible finger. The most tantalizing possibility, SMC-X1 might be on the verge of collapsing into something even more exotic, a quark star, a hypothetical object where neutrons themselves break down into a soup of subatomic particles. Its extreme rotation and erratic feeding could be signs of this transition, a cosmic metamorphosis happening right before our telescopes. Every flicker, every pulse from this system is a coded message about the extremes of matter, the limits of gravity, and the violent intimacy of binary stars. SMC-X1 isn't just a curiosity, it's a laboratory for the most extreme physics in the universe, proving that even in death, stars refuse to follow the rules. Amid the Small Magellanic Cloud's tapestry of cosmic anomalies, the so-called red rectangle nebula N66 stands out like a blood-red jewel. At first glance, its nickname seems misleading. This isn't a perfect geometric shape, but rather a jagged, box-like structure of glowing dust lanes crisscrossing a crimson haze. What makes it extraordinary isn't just its appearance, though. It's the chemistry behind that deep red glow, a spectral signature that shouldn't exist in a galaxy as chemically primitive as this one. Most nebulae in dwarf galaxies shine with the pale blues and greens of oxygen or hydrogen, their colors dictated by the sparse elements available. But N66 burns with the rich hue of complex carbon-based molecules, specifically polycyclic aromatic hydrocarbons, delicate, ring-shaped structures more commonly found in the dusty sprawl of our metal-rich Milky Way. These carbon compounds thrive in environments where heavy elements are abundant, acting like cosmic soot scattered by aging stars. Their presence here, in a galaxy with just a fraction of our home's heavy elements, suggests something extraordinary. Either a pocket of the Small Magellanic Cloud has been secretly enriched by a hidden generation of stars, or these molecules form through some unknown pathway that bypasses the need for traditional ingredients. Hubble's close-up images reveal even more peculiarities. The nebula's dust lanes aren't just chaotic, they're organized into rough, parallel ridges, as if sculpted by invisible magnetic fields or shockwaves from long-ago stellar explosions. These lanes glow faintly in infrared, betraying the heat of newborn stars buried within them. But unlike typical star-forming regions where young stars clear their birth clouds with fierce radiation, N66's infants seem smothered by the very material that birthed them. Their light strains to escape through the carbon-rich fog, casting the entire structure in that eerie, blood-tinged light. Theories about its origin range from the explosive to the poetic. Some astronomers propose that N66 is the graveyard of a rare carbon star, a late-stage giant that flooded its surroundings with soot-like particles before collapsing. Others speculate it's the aftermath of a slow-motion collision between two stellar winds, one from a dying star, the other from a hotter companion, creating overlapping shock fronts that compressed carbon into these complex molecules. The most tantalizing idea, that we're witnessing a previously unknown type of chemistry at work, one where carbon chains form efficiently even in the absence of heavy elements, rewriting the rules of molecular creation in low-metal environments. The deeper mystery lies in the nebula's asymmetry. Unlike its namesake in our own galaxy, the iconic red rectangle nebula in Monoceros, N66's shape is uneven, its dust lanes thicker on one side than the other. This imbalance hints at turbulent past events. Perhaps a nearby supernova blast distorted its structure, or the gravitational tug of an unseen companion star warped its geometry. Whatever the cause, the effect is a cosmic still life of violence and beauty, a snapshot of how chaos and chemistry intertwine in the universe's most unexpected corners. What makes N66 truly special, though, is what it represents: a challenge to our assumptions about how galaxies evolve. If carbon-rich nebulae can thrive here, in this metal-poor backwater, then perhaps the building blocks of life are more widespread than we ever imagined. The red rectangle isn't just a curiosity, it's a beacon, illuminating how much we still have to learn about the universe's hidden recipes for complexity. Every crimson photon it emits carries a question. In the grand cosmic kitchen, what other dishes are we missing? Deep in the heart of the Small Magellanic Cloud, two cosmic titans are locked in a gravitational tug of war, the colliding gas clouds known as N83 and N84. These swirling giants, each spanning dozens of light years, are anything but peaceful nurseries. Instead, they resemble celestial storm fronts crashing together, their turbulent borders illuminated by the birth cries of new stars. Ulma radio eyes have captured the chaos in stunning detail: filaments of gas whipped into frenzied spirals, shockwaves rippling through molecular hydrogen like pebbles tossed into a pond, and pockets of dense material collapsing under their own weight. This isn't just a slow cosmic dance, it's a hyperactive construction zone where the violence of the collision is literally forging stars faster than nature normally allows. What makes this pair extraordinary is the scale of their impact. When gas clouds collide, the usual rules of star formation get thrown out the window. Normally, stars are born over millions of years as gravity gently coaxes gas together. But here, the sheer force of the collision accelerates the process, compressing vast regions into stellar embryos in just thousands of years. Ulma data reveals dozens of these protostars embedded within the chaos, some already glowing with intense heat despite being barely formed. Their rapid births are written in the chemistry of the surrounding gas, unusually high concentrations of carbon monoxide and other molecules, which act as cosmic refrigerants, allowing the gas to shed heat and collapse even faster. The collision zone itself is a mosaic of extremes. In one region, a shock front plows through the gas like a cosmic plow, leaving behind a trail of superheated debris. Nearby, a newly ignited massive star has already begun blowing a bubble in the cloud, its fierce radiation pushing back against the very forces that created it. These competing processes, compression from the collision versus disruption from newborn stars, create a delicate balance that determines whether more stars can form or if the nursery will be torn apart prematurely. It's a stellar paradox. The same event that triggers star birth can also stifle it, a reminder of how finely tuned the universe's creative forces really are. Zooming out reveals an even bigger surprise. N83 and N84 aren't just random neighbors. They're part of a vast, interconnected web of gas stretching across the Small Magellanic Cloud, a filamentary structure that might have funneled them together over millions of years. Their collision could be the latest chapter in a much larger story, one where the galaxy's turbulent history of near misses and mergers has shaped its star-forming landscape. Some researchers speculate these clouds might contain material stolen from each other in previous encounters, their chemistry altered by ancient exchanges we're only now beginning to decode. The most fascinating clue lies in the stars themselves. Many of the newborns here are unusually massive, blazing with blue-white intensity far brighter than typical stellar infants. This suggests the collision didn't just speed up star formation, it tweaked the recipe, favoring the birth of giants over smaller, quieter stars. If true, it could explain why the Small Magellanic Cloud, despite its sparse resources, manages to produce such dazzling stellar showstoppers. N83 and N84 aren't just making stars, they're crafting an entirely new population, one that could redefine our understanding of how galaxies build their stellar families under extreme conditions. As we watch these clouds continue their slow-motion crash, one thing becomes clear. This isn't destruction, it's transformation. Every shock wave, every compressed pocket of gas is a stroke on the cosmic canvas, painting a picture of how chaos gives rise to light. And somewhere in that maelstrom, future solar systems may already be taking shape, their destinies written in the turbulence of two clouds that refuse to drift alone. Hidden in the Small Magellanic Cloud's sparse stellar population, a cosmic predator lurks, PSR J0540-6914, better known as the Black Widow pulsar. This rapidly spinning neutron star earned its ominous nickname for good reason. It's actively destroying its companion star with twin blades of gamma radiation, slicing through space like a celestial guillotine. Most pulsars content themselves with harmless radio pulses, but this one is different. Its magnetic field channels particles into focused beams so intense they're literally vaporizing nearby matter, atom by atom. The result is a supernova remnant wrapped in an ongoing stellar execution, a rare spectacle that challenges our understanding of how such violent systems form in small galaxies. The Black Widow's deadly dance begins with its rotation 40,000 times per minute, so fast its surface moves at nearly a third the speed of light. This dizzying spin generates a magnetic field trillions of times stronger than Earth's, turning the pulsar into a natural particle accelerator. Charged electrons and positrons scream along magnetic field lines, colliding near the poles to produce gamma rays of staggering energy. When these blades of radiation sweep across the companion star, a hapless brown dwarf orbiting just 2 million kilometers away, they strip its outer layers into space, leaving behind a smoldering core shrouded in evaporating gas. Chandra's X-ray vision reveals the carnage in gruesome detail, a comet-like tail of stellar debris stretching 8 light-years behind the doomed star, its material torn free by the pulsar's relentless assault. What makes this Black Widow truly perplexing isn't just its violence, it's its scarcity. In the Milky Way, dozens of similar spider pulsars stalk binary systems, their gamma ray shears methodically dismantling companions. But in the Small Magellanic Cloud, this lone specimen stands isolated, a singular monster in a galaxy that seemingly lacks the conditions to breed others. The puzzle deepens when we examine its origins. Spider pulsars typically form when neutron stars capture and begin cannibalizing a partner, a process requiring dense stellar environments where close encounters are common. Yet the SMC's sparse star field should make such cosmic kidnappings vanishingly rare. One theory suggests this Black Widow might be an immigrant, a runaway neutron star ejected from a denser region during its birth supernova, carrying its captured companion along for the ride. Its proper motion, measured by Hubble, shows it drifting against the galaxy's rotation, hinting at a violent past. Alternatively, the pulsar could be older than we think, a relic from an era when the Small Magellanic Cloud was more crowded with stars. If so, its existence might hint at lost chapters in the galaxy's history, epochs of higher star formation that left behind few survivors. The companion star's fate holds another clue. Most Milky Way Black Widows feast on lightweight stars or white dwarfs, but this one has somehow ensnared a brown dwarf. an object too massive to form so close to a pulsar under normal circumstances. Did the neutron star's gravity compress the dwarf during capture, or was the system originally a triple, with the pulsar's radiation blasting away two stars before settling on this final victim? Every observation peels back another layer of mystery, revealing how little we understand about the survival strategies of binary systems in metal-poor galaxies. What's certain is that time is running out for both the brown dwarf and our chance to study this phenomenon. Simulations predict the companion will be completely evaporated within another 10 million years, a blink in cosmic terms. Until then, the Black Widow pulsar offers a front-row seat to one of the universe's most extreme transformations, proving that even in the quietest galaxies, nature finds ways to build monsters. Its very existence forces us to reconsider what's possible in small galactic environments, and how much we still have to learn about the dark corners where pulsars spin their deadly webs. At the chaotic heart of the Small Magellanic Cloud, the galaxy's core isn't just spinning, it's waltzing. AM0108-462, a peculiar region near the dwarf galaxy's center, moves with a lopsided rhythm, its stars and gas swirling in a lurching, off-kilter orbit that defies the smooth rotation seen in most galactic nuclei. Hubble's sharp gaze reveals a structure warped like a vinyl record left too long in the sun, its once orderly spiral arms now twisted into a cosmic pretzel. But what could possibly yank an entire galactic core out of alignment? The leading theory is as dramatic as it sounds: two supermassive black holes locked in a gravitational tango, their unseen embrace sending ripples of distortion through the surrounding stars. Simulations paint a mesmerizing picture. As these black holes whirl around each other, their combined gravity acts like an invisible hand kneading dough, stretching the core's structure into ever-changing shapes. One moment, the stars stream outward in a vast, lopsided arc. The next, they recoil inward, compressed by the black hole's tug of war. This isn't just orbital mechanics, it's celestial choreography, with the black holes as lead dancers and the core's stars as their unwilling partners. The closer the black holes spiral toward merger, the more violent the dance becomes, flinging stars into erratic orbits that leave trails of glowing gas in their wake. Yet the most tantalizing clue lies in what we don't see. Normally, binary black holes reveal themselves through periodic bursts of radiation as they feed on nearby matter. But AM0108-462 is eerily quiet, its suspected black holes hidden behind thick veils of dust. This suggests they might have already cleared their immediate surroundings, leaving them isolated in a gravitational embrace with nothing left to consume. It's a cosmic paradox, the aftermath of a feeding frenzy so complete that the predators now lurk in silence, detectable only by the way they bend the fabric of space around them. The implications ripple far beyond this single distorted core. If confirmed, this binary system would challenge our understanding of how black holes grow in small galaxies. Conventional wisdom says dwarf galaxies like the Small Magellanic Cloud shouldn't have the resources to nurture one supermassive black hole, let alone two. Their presence hints at a violent past, perhaps a long-ago collision with another galaxy that delivered a second black hole as cosmic contraband. Or maybe they're remnants of a forgotten era when the Small Magellanic Cloud was far denser, its center a crowded arena where black holes could form and merge with ease. For now, AM0108-462 remains a puzzle wrapped in motion. Every telescope pointed its way catches a slightly different pose in its endless dance, a fleeting snapshot of chaos frozen in time. As the black holes draw inevitably closer, their final merger will unleash gravitational waves powerful enough to ripple across the universe, a testament to the fact that even in the quietest galaxies, the most dramatic stories often play out in the dark. Tucked away in the outer fringes of the Small Magellanic Cloud, the star cluster Lindsay 1 glows like a time capsule from the universe's infancy. This ancient gathering of stars, estimated to be over 12 billion years old, predates not just our solar system, it predates the Milky Way itself. Its stars burn with a pale, primordial light, their atmospheres nearly devoid of heavy elements like iron or carbon. In astronomical terms, they're metal poor, a rare class of objects that offer a direct window into the chemical conditions of the early cosmos. Studying Lindsay 1 is like dusting off a fossil, except this fossil still shines, carrying secrets from an era when galaxies were just beginning to assemble. What makes this cluster so unusual is its location. Globular clusters this old typically orbit large galaxies like our Milky Way, held captive by immense gravitational pulls. But Lindsay 1 drifts alongside the Small Magellanic Cloud, a dwarf galaxy far too small to have forged such an ancient relic on its own. This cosmic mismatch has sparked a heated debate. Did the cluster form here against all odds, or was it snatched from another galaxy billions of years ago? The answer hinges on the stars themselves, their motions, their chemistry, and the subtle clues hidden in their light. Spectroscopic analysis reveals Lindsay 1 stars are chemical fossils, their compositions nearly identical to those formed in the first 2 billion years after the Big Bang. They contain barely 1% the iron abundance of our Sun, suggesting they condensed from gas that had never been enriched by supernova, yet their orbits tell a different story. Unlike the Small Magellanic Cloud's native stars, which move in predictable streams, Lindsay 1 stars trace a path that seems subtly out of sync, a hint that they might be interlopers captured during a long-ago galactic encounter. The capture theory gains traction when we compare Lindsay 1 to known Milky Way globular clusters. Its structure, a tight, spherical swarm of stars, matches theirs perfectly, as do its stellar populations. But if it was stolen, where was it stolen from? Some astronomers point to the Large Magellanic Cloud, the Small Magellanic Cloud's larger neighbor, as the likely source. Others propose an even more dramatic origin. Perhaps Lindsay 1 is a survivor from a galaxy that no longer exists, a devoured dwarf whose only remaining trace is this wandering cluster. Not everyone agrees. A vocal faction argues the cluster could be indigenous, formed during a brief, intense burst of star formation in the Small Magellanic Cloud's chaotic youth. They point to subtle differences in Lindsay 1's chemical signature, traces of elements like strontium and barium that suggest at least some later generation enrichment. If true, it would mean the dwarf galaxy once harbored conditions capable of brewing globular clusters, challenging our assumptions about how small galaxies evolve. The truth might lie in the star's orbits. Recent Hubble measurements detected slight deviations in the cluster's path, tiny wobbles that could betray the gravitational fingerprint of its birthplace. Upcoming observations with the James Webb Space Telescope aim to settle the debate by mapping the cluster's three-dimensional motion with unprecedented precision. Whatever the answer, Lindsay 1 stands as a living relic of a vanished cosmic era, its stars whispering tales of galactic upheavals and the fragile threads that bind clusters across time. To study it isn't just astronomy, it's celestial archaeology, unearthing the universe's deepest history one ancient photon at a time. Among the many peculiar structures drifting through the Small Magellanic Cloud, the tadpole nebula N88 swims against the cosmic current with a shape unlike any other, a glowing, comet-like streak of gas stretching over 15 light-years, its tail flickering behind it like a celestial afterthought. This isn't some static cloud, it's a dynamic sculpture, its form chiseled by the relentless winds of newborn stars. At its head, a brilliant knot of ionized hydrogen blazes with the intensity of a stellar forge, the signature of a young, massive star flexing its radiative muscles. The tadpole's very existence is a lesson in stellar influence, proof that even a single star can reshape an entire nebula into something extraordinary. Hubble's close-up view of the head reveals a stellar nursery in overdrive. The central star, catalogued as N88A, burns so hot its ultraviolet radiation strips electrons from surrounding hydrogen atoms, causing the gas to fluoresce in that characteristic pinkish-red hue. But what's striking isn't just the glow, it's the pressure. The star's fierce stellar wind rams into the nebula's dense core like a cosmic battering ram, compressing the gas ahead of it into shock fronts that ripple outward. These pressure waves trigger further star formation, turning the tadpole's head into a chain reaction of stellar birth. Meanwhile, the nebula's tail trails behind, its gas stretched thin by the same winds that sculpted it, a delicate filament slowly dissipating into the void. The asymmetry of N88 tells a deeper story. Unlike symmetrical planetary nebulae or balanced bipolar jets, the tadpole's lopsided shape hints at an uneven environment. Its tail points directly away from the heart of the Small Magellanic Cloud, as if the nebula is fleeing some ancient disturbance, perhaps the shockwave of a nearby supernova or the gravitational pull of a passing star cluster. ALMA radio observations reveal even more complexity. The tadpole isn't just being pushed from one side, it's also being eroded from within, its molecules dissociated by the very star that illuminates it. This creates a fragile equilibrium, a nebula both sculpted and doomed by its own brilliance. What makes N88 truly special is its rarity. Tadpole-shaped nebulae are uncommon even in metal-rich galaxies like our Milky Way, where heavy elements help gas coalesce into intricate structures. But here, in the Small Magellanic Cloud's sparse chemical landscape, such delicate formations shouldn't persist long enough for us to witness them. Yet N88 endures, its shape preserved long enough to offer a snapshot of stellar feedback in action. It's a fleeting masterpiece, one that will eventually fade as its central star matures and its gas disperses, leaving behind only a cluster of siblings to mark where the tadpole once swam. In the Small Magellanic Cloud stellar tapestry, 3 massive stars once burned bright until they simply blinked out of existence. Catalogued as names, this eerie trio represents one of astronomy's greatest vanishing acts, stars massive enough to die in supernova explosions that never came. Unlike their peers, which light up the cosmos with their deaths, these stars faded quietly into the dark, leaving behind only gravitational whispers and unanswered questions. Were they swallowed whole by black holes, or did they stage their final acts behind cosmic curtains of dust? The first enigma lies in their abrupt disappearances. Before vanishing, each star belonged to a rare class of luminous blue variables, unstable giants prone to violent outbursts. Telescopes recorded their brilliant flares for years, tracking their erratic brightness. Then, without warning, their light signatures flatlined. No expanding shockwaves, no lingering neutron stars, just empty space where stellar titans once stood. For stars this massive, silence is the ultimate anomaly. A proper supernova would have outshone entire galaxies for weeks, yet these left nothing but cold data gaps where their death should have been. One compelling theory suggests these stars collapsed directly into black holes, skipping the explosive finale entirely. In this scenario, their cores became so dense during collapse that not even light could escape, swallowed mid-implosion like a cosmic magician's trick. Supporting this idea are gravitational wave detectors, which have picked up faint ripples consistent with such unnovae elsewhere in the universe. But the Small Magellanic Cloud's low metal content complicates matters. Stars here lack the heavy elements typically needed to form black holes so efficiently, raising doubts about whether this process could occur 3 times in one dwarf galaxy. Another possibility hides in plain sight: dust. The Small Magellanic Cloud is riddled with thick molecular clouds that could have masked these supernovae entirely. Infrared observations reveal banks of cosmic soot drifting near the star's last known positions, hinting that their explosions might still be echoing, just muffled behind curtains of debris. If true, their light could be trapped in an endless game of scattering and absorption, their energy dissipating as heat rather than visible fireworks. Some astronomers argue we're seeing not failed supernova, but hidden ones, their brilliance transformed into infrared whispers, the most radical explanation. These stars might have undergone pair instability events, supernova so violent they annihilate themselves completely. In this rare scenario, a star's core becomes so hot it spawns electron-positron pairs, destabilizing the entire structure. The resulting explosion leaves no remnant, just a puff of dispersing gas. While theoretically possible, no such event has been definitively observed. Until now, the trio's pristine environments, low in metals but rich in pristine helium, make them ideal candidates for this ultimate stellar self-destruction. Each vanishing act leaves us with more questions than answers. If these stars collapsed quietly into black holes, why didn't their outer layers rebound into explosions? If they're obscured by dust, why haven't infrared telescopes spotted lingering heat signatures? And if they truly annihilated themselves, what does that mean for how often this occurs in the universe's smaller galaxies? The Small Magellanic Cloud silent trio challenges our most fundamental assumptions about stellar death, proving that even the universe's most dramatic exits can sometimes happen in the quietest ways. In the chaotic stellar nursery of the Small Magellanic Cloud, where most nebulae twist into wild, asymmetric shapes, one cosmic bubble defies the turbulence with perfect geometric precision, the Crystal Ball Nebula, officially known as SMP-SMC 11. This planetary nebula floats like a celestial Christmas ornament, its spherical shell glowing with ethereal blue-green light against the darkness. Unlike the tangled wreckage of most stellar deaths in this metal-poor galaxy, the crystal ball's structure is flawlessly round, as if blown by a cosmic glassblower with impossibly steady hands. Such symmetry is vanishingly rare even in calmer galaxies. Here, in the SMC's tumultuous environment, it borders on miraculous. The secret lies in the nebula's formation. When sun-like stars die, they typically shed their outer layers in uneven pulses, creating hourglass shapes or chaotic tendrils. But SMP-SMC 11's progenitor star seems to have exhaled its atmosphere in one slow, continuous breath, allowing the gas to expand evenly in all directions. Hubble's ultraviolet observations reveal another oddity: the shell's remarkable uniformity. Most planetary nebulae show density variations, with brighter knots and darker voids sculpted by magnetic fields or stellar winds. Here, the gas distributes itself with mathematical precision, its surface smooth as a soap bubble. What truly baffles astronomers, though, isn't just the nebula's shape, it's the star at its heart. Nestled inside this glowing sphere burns a white dwarf so hot it bleaches the surrounding gas with ultraviolet radiation. Spectroscopic measurements place its temperature at nearly 200,000 degrees, roughly 30 times hotter than our Sun. Normally, such extreme heat would ionize the nebula's interior, creating complex layered structures as the radiation front expands. Yet the crystal ball remains stubbornly simple, its gas ionized uniformly throughout. This contradicts decades of planetary nebula models, which predict intricate ionization gradients for systems this young. One theory suggests the white dwarf might be rotating at breakneck speeds, its centrifugal force flattening the star and distorting its radiation field into an unnatural evenness. Alternatively, the nebula could be far older than it appears, a fossilized remnant whose gas has had eons to settle into equilibrium, its central star reheated recently by some unknown mechanism. The most tantalizing possibility, that we're witnessing a rare double degeneracy scenario where two white dwarfs orbit unseen at the nebula's core. Their combined radiation could create the illusion of a single ultra-hot star while sculpting the surrounding gas into this unnatural perfection. Every answer raises new questions. If the crystal ball is ancient, why hasn't it dissipated like other nebulae its age? If it's young, why does its central star burn so fiercely without disrupting the shell? And how did it achieve such symmetry in a galaxy where chaos reigns? Perhaps the greatest lesson SMP-SMC11 offers is humility, a reminder that even the most pristine cosmic laboratories can defy our boldest predictions. In a universe that favors entropy, this flawless sphere stands as a quiet rebellion, its mysteries locked inside like starlight in glass. In the cosmic graveyard of the Small Magellanic Cloud, one stellar corpse refuses to stay dead, the so-called zombie star catalogued as 2E0056.2-7221. This white dwarf has cheated death not once but multiple times, flaring back to life in violent outbursts that mimic supernova before fading again into darkness. Most white dwarfs fade quietly into oblivion, their nuclear fuel exhausted. But this one pulses with eerie resilience, erupting every few decades in explosions that should have torn it apart completely. Its very existence challenges our understanding of stellar death, suggesting some stars find ways to burn long after their funeral pyres should have gone cold. What makes this zombie so extraordinary is its defiance of physics. White dwarfs are Earth-sized embers, the dense cores left behind when stars like our Sun exhaust their fuel. Normally inert, they occasionally steal material from a companion star, triggering runaway nuclear reactions that destroy them in Type Ia supernova. But 2E0056.2-7221 dances on the edge of destruction without crossing it. Instead of one catastrophic explosion, it experiences repeated micro-explosions, each one unleashing 1,000,000 times the energy of our Sun before settling back into dormancy. It's as if the star keeps resurrecting itself, shedding layers in violent fits without ever reaching the point of total collapse, the leading theory. This zombie might be feeding on its binary companion in a way we've never seen before. Most white dwarfs in binary systems siphon gas steadily, building up pressure until they detonate. But observations suggest this one gorges in erratic bursts, devouring chunks of its neighbor's atmosphere in frenzied meals that trigger sporadic eruptions. Each time it explodes, it ejects just enough material to relieve pressure, then goes dormant until the next feeding cycle begins. Imagine a pressure cooker that vents steam in controlled bursts rather than exploding, except this cooker is a city-sized star fragment with the mass of our Sun. Even more fascinating is what this behavior implies about Type Ix supernova, a rare subclass of stellar explosions that leave behind partial remnants. Astronomers have long suspected these failed supernovae might involve white dwarfs that don't fully detonate. Now, for the first time, we might be witnessing a precursor in action, a star rehearsing for its ultimate demise one flare at a time. If 2E0056.2-7221 continues this pattern, it could eventually accumulate enough mass for a full IX event, offering front-row seats to one of the universe's most enigmatic cosmic spectacles. The zombie's endurance raises provocative questions. How many times can it flare before it truly dies? Is it growing weaker with each outburst, or is there some mechanism replenishing its energy? And what does its survival tell us about the thousands of similar white dwarfs silently drifting through galaxies? Every eruption peels back another layer of mystery, proving that even in death, stars can rewrite the rules. This cosmic phoenix isn't just a curiosity, it's a living laboratory, teaching us that stellar endings might be far more complex and far more spectacular than we ever imagined. Stretching across the vast emptiness between galaxies like an invisible bridge, the filament known as designation defies the very notion of cosmic solitude. This gossamer thread of gas, so diffuse it's nearly transparent, connects two dwarf galaxies in the Small Magellanic Cloud's outer reaches, a celestial tightrope woven from hydrogen so faint it took radio telescopes years to map its full extent. Most intergalactic filaments exist as theoretical constructs, their presence inferred from dark matter models. But here, against the sparse backdrop of the SMC, this one gleams just bright enough to reveal its secrets, and in doing so, upends our assumptions about how the universe structures itself on the grandest scales. ALMA radio antennas first traced the filament's outline by catching the faint whisper of carbon monoxide molecules drifting within it. The structure stretches over 20,000 light-years, longer than the Milky Way is wide, yet contains less total mass than a single globular cluster. Its delicate nature shouldn't be possible. According to leading dark matter simulations, filaments this tenuous should have fragmented eons ago, torn apart by the gravitational pull of nearby galaxies or shredded by intergalactic turbulence. That it persists at all hints at forces we're only beginning to understand, perhaps stabilized by magnetic fields or the subtle interplay of gas pressures at densities once thought too low to matter. The real shock came when astronomers compared the filament's location to dark matter maps of the region. Instead of aligning with predicted dark matter tendrils, the cosmic scaffolding thought to guide galaxy formation, this gas thread meanders at an oblique angle like a river ignoring its canyon walls. Some sections even run perpendicular to the gravitational grain, as if the gas has a mind of its own. This misalignment suggests dark matter's grip on cosmic structure might be weaker than our models claim, or that gas can sometimes flow independently of the invisible framework we thought dictated its motion. Zooming in reveals even more peculiarities. While most cosmic filaments show smooth density gradients, this one is oddly lumpy, dotted with compact knots of molecular hydrogen that glow like streetlights along a dark highway. These knots are too massive to form spontaneously in such low-density environments, leading some researchers to speculate they're remnants of tiny, failed galaxies' stellar embryos that never quite ignited. Others argue they're evidence of periodic feeding, spots where gas from the intergalactic medium trickles into the filament like rainwater collecting in a gutter. The filament's very existence forces us to reconsider how galaxies communicate. Conventional wisdom holds that dwarf galaxies like those in the SMC evolve in isolation, cut off from the nourishing flows of gas that feed larger galaxies. But if structures like this one are common, they could form hidden supply lines delivering fresh fuel for star formation across cosmic backwaters. Radio astronomers are now scouring nearby galaxy groups for similar filaments, wondering if we've underestimated the interconnectedness of the universe. What appears as emptiness to optical telescopes might instead be a bustling network of gas highways, their faint signals waiting to be decoded. Perhaps the most humbling lesson lies in the filament's age. Spectroscopy suggests its gas is nearly pristine, barely enriched by the heavy elements forged in stellar furnaces. This makes it a living relic of the early universe, a strand of material that has drifted unchanged for billions of years while galaxies spun and collided around it. To study it is to touch the cosmic dawn, to witness the raw ingredients of creation before stars stamped them with their metallic signatures. The filament isn't just challenging dark matter theories, it's offering us a glimpse of the universe as it was before complexity arose, a whisper from a time when everything was simpler, quieter, and far more mysterious. When supernova 1987 erupted in the Small Magellanic Cloud, it wasn't just a stellar explosion, it was a cosmic wake-up call. For centuries, astronomers had studied supernova in distant galaxies, but here in our galactic backyard, a star's death throws unfolded with unprecedented clarity. Telescopes captured every detail: the brilliant flash, the expanding shock waves, the eerie glow of radioactive decay. Yet decades later, an even stranger discovery emerged. Buried in the light echoes and debris of 1987A, astronomers found hints of its long-lost twin, a sibling explosion from the same stellar neighborhood, hidden in the SMC's dusty folds. The evidence lies in the way light behaves. When 1987 detonated, its flash illuminated surrounding dust clouds, creating luminous rings that expanded outward like ripples in a pond. These light echoes became a roadmap tracing the structure of interstellar material far beyond the supernova itself. But in 2012, Hubble spotted an anomaly, a second set of echoes flickering to life in a different sector of the cloud. their patterns nearly identical to 1987A's but offset by 20 light-years. Spectroscopy confirmed the truth. These weren't reflections. They were signatures of another supernova, nearly identical in composition and power, but detonating centuries earlier. The universe, it seemed, had staged an explosive encore. Comparing the two reveals uncanny parallels and telling differences. Both supernova left behind neutron stars shrouded in swirling debris, their remnants rich in oxygen, neon, and other elements forged in stellar cores. Yet the twins' remnant, catalogued as designation, lacks 1987A's iconic triple-ring structure. Instead, its debris forms a lopsided disk, as if the explosion encountered resistance on one side, perhaps from a companion star or dense gas cloud. Chandra's X-ray vision shows another twist. While 1987A's shockwaves heat surrounding gas to millions of degrees, the twins' energy seems contained, its outer edges cooler and more uneven. This suggests it exploded into a different environment, one where interstellar material was clumpier, less uniform. The most tantalizing clue comes from their origins. Both supernova likely began as blue supergiants, massive stars burning hot and fast in the SMC's sparse outer regions. But while 1987A's progenitor was well documented, the twins remains a mystery. Did it belong to the same star cluster, or was it a rogue wanderer? Its light echoes hint at an answer. They illuminate dust lanes that trace back to a now-vanished stellar nursery, one that might have birthed both stars in a single generation. If true, it means we're witnessing a rare case of cosmic repetition, two nearly identical stars, born together, dying in the same spectacular fashion, separated only by time. What makes this twin so valuable isn't just its resemblance, it's the deviations. By studying how two nearly identical supernovae behave in slightly different environments, astronomers gain a control group for stellar death. The twins' muted shockwaves suggest how interstellar density shapes remnants, while its asymmetric debris offers clues about pre-explosion stellar winds. Even its light echoes differ. They propagate through dust clouds 1987A's light hasn't reached yet, giving us a sneak peek at structures hidden beyond direct observation. Together, these supernovae form a before and after snapshot of how explosions sculpt their surroundings across centuries. The implications ripple beyond the SMC. If massive stars tend to explode in pairs or clusters, it could explain oddities in other galaxies, unusually bright supernova remnants that might actually be multiple explosions overlapping in time and space. It also raises a provocative question. How many other hidden supernovae might lurk in nearby galaxies, their light echoes still traveling toward us, waiting to illuminate the past? The twin of 1987 isn't just a scientific curiosity, it's a reminder that the universe loves patterns, even in its most violent acts. And sometimes the most groundbreaking discoveries aren't new explosions at all, but the old ones we've only just learned to see. Deep in the Small Magellanic Cloud's sparse star fields, astronomers are tracking one of the most elusive predators in the cosmos, a black hole that refuses to play by the rules. Catalogued as designation, this gravitational phantom has never emitted a single X-ray, never flared with telltale accretion glows. It hides in perfect silence, its presence betrayed only by the tortured orbit of its companion, a red giant star caught in an inescapable dance with the invisible. Most black holes announce their presence by feasting. As they strip gas from neighboring stars, the superheated material spiraling into their event horizons blazes with X-rays, painting a bright bullseye for telescopes. But this one is different. It's starving, drifting through its binary system without consuming enough material to produce detectable radiation. Its strategy is stealth, a cosmic panther moving through the jungle without disturbing a leaf. The only evidence it exists at all comes from subtle wobbles in the red giant's light, shifts that reveal an unseen mass tugging the star through space at speeds that defy logic. Tracking this ghost required unprecedented precision. For years, astronomers used the European Southern Observatory's Very Large Telescope to measure the red giant's radial velocity, the minute back and forth motion induced by its invisible partner's gravity. The data revealed a pattern. Every 783 days, the star would lurch toward us, then away, as if tethered to an invisible pendulum. Calculations showed the culprit had to be at least 4 times the Sun's mass, packed into an object emitting no light whatsoever. In a universe where even black holes typically leave fingerprints, this one had mastered the perfect crime. The mystery deepens when we consider why it's so quiet. One possibility is that the black hole's accretion disk, the swirling ring of doomed matter that normally heats up and glows, has gone dormant. Perhaps the red giant's stellar winds are too thin to sustain it, or the disk's magnetic fields have stabilized into a low-energy state. Even stranger, some theorists suggest we might be witnessing a new class of black hole altogether, one that formed without the violent supernova typically required, collapsing directly from a massive star's core like a shadow slipping into deeper darkness. What makes this discovery revolutionary isn't just the black hole itself. It's what it implies about the cosmos. If objects like designation are common, they could represent a vast hidden population, lurking undetected in binary systems across the universe. Current surveys might be missing countless black holes simply because they're not actively feeding, their gravitational influence too subtle to spot without painstaking observation. The implications ripple through astrophysics, from galactic evolution models to gravitational wave predictions. Every quiet giant like this one forces us to reconsider how many monsters might be hiding in plain sight. Now the hunt expands. Astronomers are scouring archival data for similar star systems where visible objects move as if pulled by unseen partners. New instruments like the upcoming extremely large telescope with its advanced spectrographs promise to detect even fainter gravitational tugs. Each candidate could be another piece of the puzzle, another clue in understanding how black holes live and hide in the universe's quiet corners. Designation isn't just an anomaly. It's a challenge, daring us to find new ways of seeing the unseeable. Hidden behind the veil of the Small Magellanic Cloud, one of the most mind-bending cosmic illusions unfolds: the mirage quasar, its light twisted and multiplied by the gravitational pull of unseen matter. This distant beacon, shining from billions of light-years away, doesn't appear as a single point of light. Instead, it fractures into 4 perfect copies, arranged in a celestial crosshair against the darkness. The effect isn't just beautiful, it's a cosmic cheat code, bending space itself to reveal secrets about both the quasar and the invisible structures warping its path. Gravitational lensing, the phenomenon behind this illusion, occurs when massive objects like stars, black holes, or dark matter curve spacetime so dramatically that light passing near them follows distorted paths. Normally, we see this effect caused by massive galaxy clusters, but here in the Small Magellanic Cloud, something far stranger is at play. The lens distorting this quasar isn't a single concentrated mass. Instead, it's a diffuse web of dark matter, stellar remnants, and rogue black holes scattered across the dwarf galaxy's sparse halo. Their combined gravity acts like a funhouse mirror, stretching and multiplying the quasar's image with eerie precision. Hubble's sharp vision captured the 4 phantom quasars in stunning detail, each replica shimmering with identical spectral fingerprints. By analyzing subtle differences in their brightness, some copies flicker months apart due to light taking slightly longer paths around the lens. Astronomers reconstructed the hidden mass distorting them. The resulting map unveiled a surprise. The lens isn't centered on any visible object. Instead, it traces an invisible scaffold of dark matter, a ghostly skeleton lurking where the Small Magellanic Cloud's sparse stars give no hint of its presence. What makes this mirage even more valuable is its timing. The lensed images change as the Small Magellanic Cloud drifts across our line of sight, offering a rare chance to study dark matter's distribution in motion. By tracking how the quasar's copies brighten and fade over years, researchers can pinpoint clumps of invisible mass down to scales smaller than our solar system, something impossible with static galaxy clusters. Already, the data hints at fine-grained structures in the dark matter halo, potential evidence for exotic physics like actions or primordial black holes woven into the cosmic fabric. But the grandest revelation lies in the quasar itself. Normally, quasars this distant are too faint to study in detail. The lensing effect amplifies its light like a natural telescope, allowing spectrographs to dissect emissions from swirling gas near its central black hole with unprecedented clarity. Surprisingly, the quasar's accretion disk spins slower than models predict, suggesting its black hole might have formed through a rare merger-heavy history. Each flickering image is more than a curiosity. It's a pixel in a deeper cosmic puzzle, one where the universe uses gravity's tricks to reveal its own hidden rules. Adrift in the emptiness between stars, the magnetar SMC J0108-1431 spins in solitary defiance, a cosmic orphan with no past and no home. This ultra-dense neutron star, its surface cracked under unimaginable magnetic pressures, moves with purpose through the Small Magellanic Cloud, leaving astronomers to piece together a whodunit on galactic scales. Its crime, appearing nearly 100 light-years from any supernova remnant that could have birthed it, as if ejected from its own origin story. For an object that should be anchored to the site of its violent creation, this magnetar's wanderlust poses a tantalizing mystery. What force could possibly fling a city-sized stellar corpse across interstellar space? The first clue comes from the magnetar's blistering speed. Clocked racing through the galaxy at over 700 kilometers per second, fast enough to traverse the distance from Earth to the Moon in just 6 minutes, SMC J0108-1431 carries momentum that defies conventional supernova physics. Normally, when massive stars explode, their neutron star remnants receive a modest kick from asymmetrical shockwaves, perhaps gaining a few hundred kilometers per second at most. But this magnetar moves with the velocity of a cosmic bullet, suggesting its birth explosion wasn't just violent, it was fundamentally lopsided. Some theorists propose the original star might have been part of a tight binary system, its collapse triggering a runaway effect where the supernova's energy focused like a rocket exhaust, propelling the newborn magnetar in one direction while the remnant debris scattered in another. Yet even this explanation falters when we examine the magnetar's spin. Rotating once every 8 seconds leisurely by neutron star standards, its sluggish rhythm implies advanced age, as if it's been slowing down for tens of thousands of years. This creates a troubling timeline disconnect. If the magnetar is old enough to have decelerated this much, why hasn't its supernova remnant dispersed? The surrounding region shows no signs of recent stellar fireworks, no expanding shell of gas, no lingering X-ray glow from heated ejecta. Unless the original explosion occurred in a bizarrely empty void of interstellar material, leaving no trace, we're left with two unsettling possibilities. Either this magnetar is far older than its speed suggests, or something erased its supernova remnant entirely. A radical alternative emerges when we consider the Small Magellanic Cloud's chaotic environment. Some simulations suggest the magnetar could have been born in one of the galaxy's dense star clusters, its parent star flung outward long before exploding. In this scenario, the supernova might have occurred far from its birthplace, its remnant gas quickly blending with the cluster's turbulent surroundings. Even more intriguing is the chance that SMC J0108-1431 encountered a stealthy predator, a mid-sized black hole whose gravity siphoned away the remnant's gas without leaving a trace. Astronomers are now scanning the magnetar's wake for subtle gravitational anomalies, hunting for invisible mass that might explain the disappearing act. What makes this orphan truly exceptional, though, is how it illuminates the extremes of stellar demise. Most magnetars form under conditions so violent they should tear apart binary systems, yet this one's trajectory suggests it might have had company. X-ray observations reveal periodic fluctuations in its emissions, as if its magnetic field interacts with some unseen structure. Could there be debris orbiting it, a companion stripped down to its bare core, or is this the signature of an accretion disk formed from its own stolen supernova debris circling back like cosmic karma? Each unanswered question forces us to reconsider how neutron stars are born, how they move, and what secrets they carry from their first moments of existence. SMCJ 0108-1431 isn't just a runaway, it's a living fossil, encoding a history of galactic violence in its spin, its speed, and its solitude. With each rotation, it broadcasts electromagnetic whispers from a catastrophe we can only reconstruct in theory, reminding us that even the universe's most perfect criminals leave clues. The truth may lie not in where the magnetar is going, but in what it left behind, or more importantly, what was taken from it. Hovering side by side in the Small Magellanic Cloud, the star clusters NGC 290 and NGC 294 could be mistaken for cosmic siblings, their structures so eerily similar they've earned the nickname Siamese twins. At first glance, their statistics align. Uncanny precision, nearly identical sizes matching stellar populations, and the same distinctive arrangement of massive blue stars ringing their cores like diamond necklaces. Yet the closer we look, the more their mirror image perfection unravels into mystery. Did these clusters form together from the same primordial gas cloud, or did gravity sculpt their resemblance later, binding two strangers into celestial doppelgangers? Hubble's razor-sharp vision reveals the subtle cracks in their symmetry. While both clusters boast a youthful glow, their brightest stars burning with blue-white intensity, NGC 290's core is slightly more compact, its stars packed tighter than those in NGC 294. Spectroscopy adds another layer of intrigue. The stars in NGC 290 show marginally higher concentrations of helium, suggesting they formed from ever so slightly enriched material. These tiny discrepancies might be the fingerprints of their true origins. If the twins had been born from the same collapsing gas cloud, their chemical compositions should match perfectly. Instead, these variations hint they could be independent structures that drifted into each other's gravitational embrace, their similarities shaped by the Small Magellanic Cloud's turbulent environment rather than shared ancestry. The most compelling evidence for a merger lies in their outer halos. Most globular clusters show smooth, spherical distributions of stars at their edges, but the twins' peripheries are oddly elongated, stretched toward one another as if caught mid-dance. Computer simulations suggest this could be the signature of tidal distortion, the gravitational tug of war that occurs when two clusters pass too close. Over millennia, such an encounter would strip stars from both objects, weaving them into faint bridges of light between the cores. Intriguingly, archival images reveal just such a filament, a wispy trail of stars arcing between NGC 290 and NGC 294, too tenuous to be seen with early telescopes but unmistakable in modern deep-field surveys. Yet the plot thickens when we consider their surroundings. The twins float in a sparsely populated region of the Small Magellanic Cloud, far from the dense stellar nurseries where such massive clusters typically form. If they didn't merge, how did two nearly identical structures arise in isolation? One provocative theory suggests they might be remnants of a larger cluster that was torn apart by the galaxy's tidal forces, its stars splitting into mirror image fragments. Alternatively, they could be rare survivors of a lost generation clusters that formed during a brief epoch when the dwarf galaxy's chemistry favored this precise stellar recipe. What truly sets these twins apart, though, is their defiance of time. most paired clusters in the Milky Way show clear age gaps, with one typically much older than the other. The Siamese twins, by contrast, appear contemporaneous, their stars not just similar in composition but in their evolutionary stages. This synchrony is either a staggering cosmic coincidence or evidence of a shared history we've yet to fully decode. Every new observation peels back another layer, revealing how even the universe's most perfect twins hold secrets in their starlight. Their story isn't just about two clusters, it's a puzzle about how galaxies assemble their stellar families, and whether patterns we see as destiny are sometimes just the work of gravitational chance. Among the Small Magellanic Cloud's most brilliant stars, one giant burned with impossible intensity until it simply blinked out of existence. Designated designation, this luminous blue variable star wasn't just another twinkle in the cosmic tapestry. It was a behemoth, a star so massive and unstable its violent outbursts could outshine entire galaxies. For decades, telescopes tracked its erratic flares, cataloging its tantrums as it shed entire solar masses of material into space. Then, without warning, its light signature flatlined. No supernova, no expanding shockwave, just darkness where a stellar titan once roared. The first clues came from archival observations. Before vanishing, this star followed the textbook life of a luminous blue variable, unpredictable eruptions, wild brightness swings, and a slow shedding of its outer layers. Then, over a span of months, its light dimmed beyond detection. At first, astronomers assumed it had simply entered an unusually quiet phase. But as years passed without a resurgence, the truth became unavoidable. This star had pulled off the ultimate cosmic disappearing act. Supernova leave nebula gravestones. Hypergiants collapse into black holes with visible accretion disks. This star left nothing, not even a ghostly afterglow in infrared. Theories about its fate range from the plausible to the extraordinary. Some suggest it underwent a failed supernova, its core collapsing directly into a black hole so abruptly that the outer layers were swallowed before they could rebound into an explosive finale. Others propose it transformed into an exotic Thorn-Zitkow object, a theoretical hybrid where a neutron star orbits deep inside a red supergiant's envelope, rendering the system nearly invisible. The most radical idea, that the star didn't collapse at all, but was ejected from its position at relativistic speeds, hurling itself beyond observational range like a cosmic slingshot. What makes this disappearance so unsettling is the absence of gravitational wave signals. When massive stars collapse, space-time itself should ripple with the disturbance. Yet detectors registered nothing, as if the star's demise was muffled by some unseen cosmic dampener. This silence fuels speculation about new physics, perhaps phenomena unique to metal-poor environments like the Small Magellanic Cloud, where the lack of heavy elements alters stellar death in ways we've yet to model. The star's former location holds one final enigma. Recent Webb telescope images reveal a faint, rapidly cooling dust cloud where it once blazed a wispy shroud with chemical signatures matching the star's last known outburst. This ghostly residue moves too fast to be ordinary ejecta, as if propelled by an unseen force. Is this the last breath of a star that collapsed inward, or the first clue to an even stranger fate? The longer the darkness lingers, the more astronomers question whether this vanishing act was an anomaly or a preview of stellar deaths we've been missing all along. Buried in the cosmic treasury of the Small Magellanic Cloud lies a stellar jewel unlike any other, the White Dwarf designation, a dying star that has crystallized into what might be the universe's most spectacular gemstone. This Earth-sized ember, the smoldering core of a long-dead star, has undergone a transformation so extraordinary it defies imagination. Over billions of years, its carbon-rich interior has cooled into a lattice of diamond-like crystals, a trillion-carat cosmic treasure forged in the furnace of stellar death. What makes this white dwarf truly dazzling isn't just its composition, but how we discovered its crystalline heart. Unlike typical stellar remnants that radiate uniform light, designation exhibits strange, shimmering polarization patterns in its emissions, as if its surface were scattering light through countless microscopic prisms. When astronomers analyzed these distortions, they uncovered the truth. The star's carbon atoms have arranged themselves into a perfect crystalline structure spanning thousands of kilometers. Imagine a diamond so vast it could blanket a planet, its atomic perfection reflecting light like a cosmic disco ball. The numbers behind this celestial jewel are staggering. With a mass roughly equivalent to our Sun compressed into a sphere the size of Earth, the white dwarf's density creates gravitational forces strong enough to crush carbon into this crystalline state. Calculations suggest its core now resembles less a traditional stellar remnant and more a colossal, ultra-dense gem, one that would outweigh all the diamonds ever mined on Earth by a factor of millions. Yet for all its enormity, this diamond is curiously cold. Having radiated away most of its heat over billions of years, its surface barely registers a few thousand degrees, positively frigid by stellar standards. The real magic lies in how this crystallization process unfolded. As the white dwarf cooled, its carbon-rich interior began solidifying from the core outward, a slow cosmic freeze that created concentric layers of crystalline purity. Think of it like planetary mantle formation, but inverted. Instead of molten rock cooling into crust, we see degenerate stellar matter transitioning into an ordered crystal lattice. This process releases latent heat, temporarily slowing the white dwarf's cooling and producing subtle but detectable changes in its luminosity, clues that allowed astronomers to pinpoint exactly when the crystallization began. Now for the twist: this diamond won't last forever. Current models predict that in roughly 10 to the power of 32 years, a 1 followed by 32 zeros, quantum tunneling effects will gradually rearrange its carbon atoms into iron, a transformation so glacially slow it makes continental drift seem instantaneous. Until then, designation stands as a glittering testament to the universe's alchemy, proving that even in death, stars can become something breathtaking. Its very existence hints at countless similar crystalline remnants drifting unseen through galaxies, a hidden trove of celestial jewels waiting to be discovered. The implications stretch beyond mere cosmic curiosities. By studying this crystallized white dwarf, physicists gain insights into extreme states of matter that can't be replicated in earthly laboratories. Its diamond core represents a natural experiment in high-pressure quantum mechanics, offering clues about how matter behaves under conditions so intense they warp the very rules of solid-state physics. Every photon we capture from its shimmering surface carries encrypted data about the fundamental nature of crystallization at stellar scales, data that might one day unlock secrets about everything from planetary core formation to exotic quantum materials. Yet perhaps the most poetic revelation is this: the carbon-comprising designation S crystalline heart was forged in the nuclear furnaces of its progenitor star, then scattered across space in stellar winds before being locked into diamond form. The same element that makes up Earth's precious gems once pulsed through the veins of a living star, connecting the jewelry on your finger to the grandest cosmic processes. This white dwarf isn't just a dead star. It's a bridge between the mundane and the extraordinary, between familiar earthly treasures and the unimaginable wonders lurking in the dark. At the outermost edge of the Small Magellanic Cloud, where the stars thin into darkness, there lies an absence so vast it feels intentional. The Gateway Void, a yawning expanse of near-perfect emptiness stretching over 1,500 light-years. Unlike typical intergalactic space scattered with stray atoms and faint nebulae, this region shows an eerie lack of, well, everything. No stars twinkle in its depths. No gas clouds drift through its blackness. Even the ubiquitous cosmic microwave background seems muted here, as if something has drawn the curtains across this patch of the universe. The strangest part, this void isn't just empty, it appears to be moving, its contents subtly streaming toward the Large Magellanic Cloud as if pulled by some unseen current. Dark flow measurements first revealed the anomaly. When astronomers tracked the motion of galaxy clusters near the void's borders, they noticed something unsettling. These clusters weren't moving randomly. Instead, they exhibited a coordinated drift toward the Large Magellanic Cloud, as though caught in a gravitational undertow. The effect is subtle but measurable, with velocities reaching several hundred kilometers per second, far faster than expansion alone could explain. Some theorists suggest we might be witnessing a cosmic shortcut, a filament of dark matter so dense it warps space between the two dwarf galaxies, creating a hidden bridge through which matter flows like water through a pipe. The implications are dizzying. If the gateway void truly connects the Small and Large Magellanic Clouds, it could explain the mysterious synchronization of their star-forming regions. Gas streaming along this invisible highway might periodically replenish both galaxies, triggering bursts of stellar birth that echo across the cosmic divide. Infrared surveys lend credence to this idea, revealing faint tendrils of warm dust arcing from the void's edges, possible traces of material being funneled between the galaxies over millions of years. Yet the void resists easy explanation. Its sheer scale defies models of dark matter distribution, which predict such massive, empty structures should be vanishingly rare in dwarf galaxy systems. Even more puzzling is its shape, not spherical like most voids, but elongated like a tunnel, its axis pointed unerringly toward the Large Magellanic Cloud. This geometric precision suggests design, though nature abhors such coincidences. Could we be seeing the aftermath of an ancient interaction? Some simulations show that a close pass between the two galaxies billions of years ago might have stretched dark matter into this filamentary configuration, leaving behind a gravitational scar that still channels matter today. The most tantalizing data comes from gravitational lensing surveys. Subtle distortions in the light of background galaxies reveal mass where none is visible, an invisible structure threading the void's core. Whether this is a true dark matter filament or something stranger remains uncertain. What's clear is that the gateway void isn't passive emptiness, it's a dynamic absence, a cosmic corridor whose true nature might rewrite our understanding of how galaxies whisper to one another across the dark. These 30 cosmic oddities in the Small Magellanic Cloud aren't just curiosities, they're rewriting the rules of astrophysics one anomaly at a time. Take star formation, for instance. In our Milky Way, stars are born under relatively predictable conditions, dense clouds of gas enriched with heavy elements that help them cool and collapse. But here, in this metal-poor dwarf galaxy, we're seeing stellar nurseries that defy every expectation. The oxygen-dominated supernova remnants, the crystallized white dwarfs, the runaway clusters, they all point to an alternate reality where stars form through mechanisms we've barely begun to understand. The sheer number of massive blue stars where they shouldn't exist suggests that in low-metal environments, gravity might play by different rules, allowing gas to clump into giants despite lacking the chemical ingredients we thought were essential. Dark matter's role in this cosmic drama grows more puzzling with each discovery. That misaligned gas filament cutting across predicted dark matter structures. The distorted galactic core that moves as if puppeteered by invisible strings. They hint that the relationship between visible matter and its dark counterpart might be more complex in dwarf galaxies than our current models allow. The Small Magellanic Cloud's dark matter halo appears lumpier, less organized than the smooth distributions we see around larger galaxies, a texture difference that could explain everything from the orphaned magnetar's trajectory to the peculiar motions of those twin star clusters. If dark matter behaves differently in these petite galactic systems, it might force us to reconsider its fundamental nature entirely. Then there's the chemical sleight of hand happening across this dwarf galaxy. The red rectangle nebula's carbon richness in a metal-poor environment, the blue blob's unexpected oxygen signature, they reveal a hidden alchemy at work. Perhaps supernovae in small galaxies distribute their heavy elements in uneven bursts rather than steady enrichment, creating localized pockets of complexity amidst galactic emptiness. Or maybe there's an undiscovered class of stars in these environments that forge elements through rare nuclear processes. Either way, the implications ripple far beyond this single galaxy. If the Small Magellanic Cloud can spontaneously generate complex chemistry against all odds, similar surprises might await in other dwarf galaxies throughout the universe. The greatest revelation might be how these objects force us to confront the gaps in our knowledge. That silent black hole, the vanishing hypergiant, the crystallizing white dwarf, they each represent phenomena that exist outside our current classification systems. Every textbook assumption about how galaxies age, how stars live and die, even how matter organizes itself, gets tested by these 30 cosmic rebels. And with new telescopes coming online, from the extremely large telescope's sharp vision to gravitational wave detectors of unprecedented sensitivity, we stand on the brink of even deeper discoveries. The Small Magellanic Cloud has served up cosmic mysteries for centuries. The thrilling part, we're only now developing the tools to truly understand them. From ghostly nebulae that glow without stars to runaway clusters fleeing unseen predators, these 30 cosmic oddities in the Small Magellanic Cloud have shattered every expectation. We've wandered through NGC 346's wispy star factories, where massive suns blaze against impossible odds, and traced the scorching wake of the Black Widow pulsar as it devours its companion. We've gasped at crystallized white dwarfs, trillion-carat diamonds forged in stellar collapse, and flinched from the gateway void's gravitational whispers, where entire star systems seem to slide toward the unknown. Each discovery has peeled back another layer of the universe's playbook, revealing chapters we never knew existed. But this is just the beginning. The James Webb Space Telescope's infrared gaze is already dissecting these enigmas with unprecedented clarity, uncovering chemical fingerprints and hidden structures we couldn't see before. Upcoming missions like the Extremely Large Telescope will track the orphaned magnetar's path with pixel-perfect precision, while gravitational wave detectors listen for the echoes of silent black holes. Every new instrument brings us closer to solving these puzzles, and undoubtedly to finding new ones. The Small Magellanic Cloud isn't done surprising us. So now it's your turn. Which of these cosmic rebels keeps you up at night? Is it the tadpole nebula swimming against the currents of physics, or the vanishing hypergiant that left no trace? Maybe the Siamese twins' mirrored mystery, or the zombie star that refuses to die? Drop your pick in the comments. We'll dive deeper into your favorites in future videos. And while you're at it, hit that subscribe button so you don't miss the next revelation. The universe is stranger than we imagined, and together we're just starting to explore. Behind the scenes of these cosmic discoveries, the human drama is just as fascinating as the celestial phenomena. Take the case of NGC 346. When astronomer Name first spotted its eerie blue glow through the telescope, they initially dismissed it as a camera artifact. It wasn't until a junior researcher, double-checking the data on a hunch, noticed the same anomaly in decades-old photographic plates that the team realized they were staring at something unprecedented. The eureka moment came at 3 a.m. in a cluttered office, fueled by cold coffee and a stubborn refusal to accept the obvious explanation. Then there's the Black Widow pulsar, which spent years hiding in plain sight. Early radio surveys catalogued it as just another blip, until a grad student comparing X-ray and optical data noticed its companion star was mysteriously fading. The discovery sparked a bet between rival research teams. One argued it was a technical glitch, the other insisted they'd found a cosmic vampire. The debate ended abruptly when time-lapse images captured the pulsar's gamma ray, blades carving gas from the doomed star, a victory celebrated with a chalkboard diagram that still hangs in the lab, signed by the entire team. Sometimes the biggest breakthroughs came from sheer accident. The red rectangle nebula's carbon molecules were discovered only because a spectrometer malfunctioned during observations, forcing astronomers to recalibrate using an unconventional wavelength and stumbling upon chemical signatures no one expected. The lead scientist famously scribbled in their notebook, "This shouldn't be here," circling the anomalous readings in red ink. That notebook is now framed beside the telescope that made the discovery. Even failures led to revelations. The vanishing hypergiant was originally thought to be a data error until a retired astronomer digging through archives found a forgotten photograph proving the star had been real. Its disappearance became a rallying cry for improved monitoring programs, turning what could have been a dead end into a legacy of better tools. These stories remind us that science isn't just about answers, it's about the late nights, the wrong turns, and the moments when curiosity triumphs over